I want to continue our conversation about double integration, but I want to start with an area problem that we can actually handle using a method we learned in Calc 2. Find the area bounded between y equals x squared minus 4 and 2x minus y. Let's start by sketching the region. So I need to sketch that parabola. It's been shifted down 4 units, and we can see it has x-intercepts at 2 and minus 2. Y-intercept down here, nice upward-facing parabola. And then I can sketch this line with a y-intercept at minus 1 and a slope of 2. And so I see the area that I want to be finding. So I need to know where these points actually live, and I think I drew it fairly well. We can kind of tell, but we might as well do it, the right way, not take anything for granted, not assume they're nice whole number coordinates. So we're going to set these two functions equal to each other. Let's get everything on one side, and that's a nice quadratic equation that even factors nicely. And so I find those intersection points are when x is minus 1 or when x is positive 3. This will let me set up my integral. And I know I need to take the top function and subtract away the bottom function. Well, I could find an antiderivative of this, but let's simplify the function first. Let's see, I'd have 2x minus x squared minus 1 plus 4 is plus 3. All right, well, I'm going to find the antiderivative, but I'm going to pretend I wrote it down in order of degrees first. That should be a 3 at the top. All right, so let's see. I have a minus 1/3 x cubed plus x squared plus 3x, evaluated from minus 1 to positive 3. All right, well, we'll plug the 3 in, and let's see. We're going to get a 27 times minus 1/3. Let's see if I can fit this in here. That's going to be a minus 9, plus 9, plus 9 more. Minus, and then I need to plug this minus 1 in. I'll get a positive 1/3, plus 1, minus 3. All right, and that's going to be a 9. And then I have 4/3 minus 3, and I do all the arithmetic, and we'll get 32 over 3. So that's that area. All right, but I said I wanted to talk about double integration, not single integration. So let's put this aside and see if we can reimagine finding that area. So I want to think about a region R in the plane. So a region R in the plane. And the double integral, that would just be 1 dA. So instead of integrating a function f of xy, I'm imagining the integrand is 1. So f of xy equals 1. So if I think about the definition of the double integral, I would divide my region R into some number of little rectangular regions. And then this double integral would be a limit as n approaches infinity of a sum from 1 to n of the little areas in there, the little delta A sub k's. Well, this sum's adding up a whole bunch of areas. So after I add up a whole bunch of areas, I would just have an area. One interesting thing to think about is I could also think about the function f of xy equals 1 saying, hey, imagine I have a plane 1 unit above the region and I take the volume of that object. Well, if I stretch this out of the plane, I would have the base area times 1 unit for length. So I'd end up with a volume that's equal in quantity to this area. But for right now, I want to think about these double integrals dA as an area. And I'd even get to use Fubini's theorem. So I come back to this example. And this time, I'm going to set it up using a double integral. So the area I'm looking for should be this double integral, where that's my region R. Fubini's theorem says I get to choose an order of integration. I think choosing y to be my first direction of integration is smart because as I shoot rays through it, I always go through the same bottom function and same top function. If I wanted to integrate with respect to x first, my function would change here, right? I have the left and right hand sides of the parabola, and then I have the line in the parabola. So I think all things point to choosing y. All right, well, I go in through the parabola and then out through the line. And then I need bounds for x to include the whole region. Because we've already set these equal to each other, I know that's -1 and 3. So we do one round of integration. And the antiderivative of 1 with respect to y is y. And I'd have x squared minus 4, 2x minus 1 dx. And then when I evaluate that, I'd have the integral from -1 to 3 of, well, I plug in the 2x minus 1, minus what happens when I have x squared minus 4 dx. And I've arrived at that problem that I've already solved. So in thinking about this region, the area of this region is a double integral, I'm really just setting up this same integral from Calc 2 using a double integral, right? I always end up after one round of integration with this same situation. And I've always enjoyed setting the problems up like this. Now, it's not actually that different from what happens in single integration. If I think about the integral from a to b of dx, well, that would be x evaluated from a to b, which is just b minus a, which is the length between b and a. So integrating dx, 1 dx gives me a length. The double integral of 1 dA gives me an area.